Hello everybody. We are going to discuss interacting state machines today. So in the previous lectures of this module, we have seen that how state machines can be designed, how they can be utilized for different kind of applications. We have also seen how sequential design can be used for effective design of or more efficient design of arithmetic circuits and in general different kind of circuits. And we have also seen how pipelining can be utilized or introduced to have efficient throughput. Now from now onwards, next 3 or 4 lectures, we will try to discuss how can we design complex systems. So in that relation, the first step is that if we have to design a complex system and let us say there are multiple state machines, how they should interact to each other, or how we can design a system which has multiple of the state machines, why these multiple state machines would be required or useful. So this is what we are going to discuss in today's lecture. So now this particular question, that if we have to design a complex system, most of the complex systems are going to be sequential systems, so I am writing complex sequential system. So if we have to design a complex sequential system, how should we start? Usually the major problem with the complex system is the detail and complexity. So because of that, sometimes designer get overwhelmed with the complexity, with the fine detail which is there in any of the complex systems. So what when we say complex system, let's consider your mobile phone, your smartphone, or any of the application which we see, let's say a smart camera, or pan, tilt, zoom, PTZ cameras. So anything which or your D2H or your smart TV. So all the applications which we have discussed in our first lecture, anything which is a digital system, overall the system will get complex. So when we are designing such a complex system, what should be the approach? First thing we have to do is we have to divide and conquer. So what does this mean? That let us divide the whole system into multiple subsystems and let's try to design individual subsystem. But now the question comes that if the subsystem has to be designed individually, but it's a part of a system, so that means it must be interacting with the other systems also, other subsystems also. How to take care of that? So whenever we have started designing these subsystems, we have to clearly define the interface, how two subsystems will interact with each other. If we have defined their interfaces clearly, then it would be easy to design each subsystem individually and then we can combine. So what is the meaning of interface here? Interface would have different meaning in different kind of systems. So let's say if you're creating a huge software and then you would like to divide things into multiple subsystems, then the interface is going to be API, application programming interface, or basically the function calls, their parameters and their arguments, list of arguments and their behavior. But in case of a hardware system or a digital system, the interface clearly means that how many inputs, how many outputs, what are the bit width of each input and each output. What is the functionality expected from each input and output, or in other words, when any particular input would be 1 and when any particular input would be 0. So also try to understand that when we are creating these subsystem interfaces, these interfaces are not visible at the system level, and usually from the user end specification they will never define the interface of subsystem. They will only say that in the end we would like to have this. So for example, if you want to have a mobile phone, so in the mobile phone they just would like to say that these are the keypad and these are the few buttons which will have. But internally, how are you going to design this mobile phone or hardware for mobile phone? It's all up to us. So how these interfaces of subsystem is going to be, it depends on the designer. So, and that makes things easier as well as complicated. Easier because it is there in our hand, complicated because now they are linked with each other. Unless we know the functionality of each subsystem, we will never able to define what is the interface. So the first exercise should be that clearly define what subsystems would be, and what would be this what would be the functionality of each subsystem, what would be expected from this subsystem to from the outside world of this subsystem, and what this subsystem is going to deliver to the outside part of this subsystem. So today we'll try to understand this concept of subsystem with the example of multiple state machine problem. So let's say a particular system can be divided into multiple state machines, and how those state machines could be segregated and how they could interact with each other. Okay, so in later lectures we will see how data path and control path could be segregated, and how we can design the control path using state machines, and how data path can be controlled using these state machines. We'll take a couple of more examples for these subsystem based or some relatively complex sequential systems. So to understand this, let's take one problem. Now this problem is very similar to our sequential matching, sequence matching problem, or a pattern matching problems which we had done in previous few lectures. So like those pattern matching problems, it's also a single input and single output. Single input means it's a serial input which is coming clock cycle after clock cycle, and there is a output every clock cycle. Now the pattern which you have to match is 1 1 0 1, and this pattern is could be overlapping in nature. So that means there could be a sequence of this 1 1 0 1 and two patterns can overlap. Now along with that, there is also one more constraint, that we have to match in the block of 256 bits. Okay, so what could be a real life analogy with this 256 block? So you know, when for example when there is a serial interface like USB, and then there would be a packet. Packet means whenever these sequence of bits are sent, these sequence of bits are sent within certain block. So all the time the data size is going to be fixed. So let's say that data size is 256 bits. So that means this block does not interact with the other blocks. So that means whatever pattern would match at the boundary will not make sense. So that's why we have to match it within the block of 256 bits only. So when this block will end, that means the pattern has not matched. In other words, pattern cannot cross the boundaries. So if we have to design such a system, it is clearly seen from our experience of this pattern matching and sequential design. So we see that we can do it using a state machine. So if we have to do it using a state machine, again from our experience, it appears that we have to remember what are the previous 3 bits. So it's a 1 1 0 1 is the pattern. So that means I should know that when none of the bit has matched, when 1 bit has matched, when 2 bits has matched, when 3 bits has matched. So at least these 4 states has to be there. And along with that, I also have to remember that how many bits has already elapsed, or how many bits of the block we have already seen. So because now number of bits in a block is 256, so there has to be some 256 states for all of these possibilities. Along with that, now I also have to remember that how many bits of the pattern has matched. So you see, try to see this information. You will see that these two information is a disjoint piece of information. So one information, how many bits has elapsed, how many which particular bit of this block it is, has nothing to do with what pattern it has already matched. So because of that, because of independent nature of these two pieces of information, total number of states in my my single state machine is going to be 4 into 256. So that means each state would remember that how many information, or basically how much bits of the pattern it has matched and which particular bit it is. So total number of states are going to be 1024. And also you can just look at this and try to understand, try to see the complexity of the state machine. How many edges would be there, and who will whenever who would design this particular problem, it won't be possible onto paper and pen, using paper and pen. We would require some sophisticated software which would probably automatically generate that which particular state should go next and which particular state should be the new one. Okay, and when the input is there, so based on that input, which particular state out of that 1024, which state it has to go. So designing itself is a challenge, and representing and then implementing it using flip-flops is whole together a sophisticated issue. So but the good thing about this particular problem is that these two pieces of information is disjoint. So can we have two different state machines? One state machine which remember how many bits has already passed, or the current bit is which particular bit of my block. The second state machine just try to see that how many bits has already matched. So these two state machines could be a different state machines. Now let's look at let's try to say that the first state machine, which is just counting how many bits has been received, let's call it M1, and M2 is the bits which is remembering the pattern of the bits, how many bits has already matched. Okay, so now what would be the interaction between these two state machines? In this case, this M1 state machine, which is saying that how many bits has been received, when the last bit or 256th bit has been received or is received, so at that time it has to send a signal to M2. It has to tell the other state machine that yes, this is the last bit, go ahead and do whatever you wish. Okay, so this information is sufficient for the second state machine to act upon and to work in such a way that the final problem, whatever is given, can be solved. So let's draw it using a diagram. So one will say that this M1 is a these are the two state machines. This is M1 and this is M2. M1 is counting the bits. Okay, so how many bits has already been received, and M2 is a pattern matching. So it's trying to match the pattern. Now both of them are given clock signal. This is the first one because it is just trying to remember that how many bits has already come, and because we are assuming here that every cycle there would be a new information. So it doesn't require to know that whether the information is 1 or 0. So the only input is clock. So at every edge of the clock, it can say that which particular bit it is. So it will keep on counting, so that this can be implemented using a counter. While the second state machine will have an input which will say that when this counter is full, or when it has reached the total threshold of the size of the block, that means 256, and then it will raise a signal which is F, and then this F signal would be 1, otherwise it is going to be 0. The other input of the pattern matcher would be the original input Y, and the output is going to be Z. So as said initially in this lecture, so this f is not visible to the outside system. To the outside system, only y is the input and z is the output, along with this being a clocked system or a synchronous system. Okay, so now when we have to design, so we can design these M1 and M2 individually. Okay, so let's try to see how can we design. So the M1 is straightforward, that because it doesn't have any input and only f is the output. So what we can do is we can simply make it a state machine, which is a counter S0 to S1, then S2, then S3, then S4 up to S255, and in all other cases output is going to be 0, but only when state is the final 255 state, then the output is going to be 1. So that means all the inputs has already received. Okay, so now when even we try to design it using using Moore's law, using Moore machine, or this is essentially a Moore machine, because there is no input and output depends on which state it is. Okay, so this can be represented using Moore machine also, but here the representation is a Mealy machine, but ideally it's a Moore machine. So just the matter of representation. So even if we use the method of implementing using our flip-flop and using next state equations, it will turn out to be a counter. Okay, now what about the second machine? So the second one actually it will take, is going to take f as well as y as an input and z as output. So to make it simple, what I am trying to do first is that let's ignore the f, let's take y as an input and z as output. So when we take y as an input and z as output, so it's a traditional state machine which is trying to identify pattern 1101 and which is overlapping in nature. So by doing this, I am trying to segregate the effect because of this M1 state machine onto my M2 state machine. Okay, so just try to remember the pattern is 1101. So from S0 state, which is my initial state, if 1 is there, then I'll move to S1 state, output is 0. When another one will come, I'll move to S2 state, output is 0. When 0 will come, I'll move to S3 state, and then another one will come, then I have to move to S1 state, because at least one of the one has been identified. So output is 1. So this way we are able to identify our pattern 1 1 0 1. Okay, so now this pattern has been there, so has been detected. So again, using the way we were designing the state machine, so let's try to complete the state machine, means try to identify that what would happen if the input is other inputs are there. So at S0, if 0 is there, because it's already a reset state, if 0 is there, it will again go back to S0 state. At S1 essentially represent that first bit of the pattern 1 has been matched, so that means another 1 will come, it will go here, but if 0 will come, then it has to go to S0 state. So it has to go to 0 state with the output 0. So in case of S2, if 0 will come, it's going to S3 state, but if 1 is coming, then it has matched at least 2 bits, 1 1. So that means it will still remain at S2 state. Output is going to be 0. In case of S3, if we have 0 as an input, 1 as an input, then we are going to S1 state. If 0 is the input, so that means it will become 1 1 0 0. So that means we have to again go back to S0 state, that means initial state with the output 0. So this exercise we have done multiple times for the other state machine. So this is the way we will do for this also. Now the next thing is that we have to consider if this f, which is generated by M1 state machine, that also is given as an input here. Okay, so if that is given as an input, what would be the effect? So first thing is that if f is 1, so that means I have reached 255 states, so that means it is the end of the block. So that means whatever is my present state, it doesn't matter. Whatever is my present state, I should write here present state. So irrespective of the present state, whatever is the present state, whether it is S0, S1, S2, S3, next state is always going to be 0, because that would be the starting of the next block. Because it is starting of the next block, so that means we have to start afresh. Okay, so and also whatever is the value of y could be 0, y could be 1, but the next state is always going to be S0 if f is 1. So that is one thing. The other thing is that if f is 1 and the present state is S3, also y is 1, then output could be 1, but the next state is going to be S0. Okay, so there could be different outputs, but the next state is going to be always S0 if f is 1. Okay, but if f is not 1, then the state machine will work like a regular state machine, whatever we have decided or whatever we have designed in our previous slide. So that means it would look like a regular state machine even without f. So with this kind of a discussion, now we can redraw our state machine and see how will it look like. So now instead of we'll start with again S0 state. Now there are two inputs. Remember, one input is f, the other input is y, and I'm writing it like f first and then y. So that means if my input is 0, 0 corresponds to f and 1 corresponds to y. So if it is 0, 1, then the next state is going to be S1. If it is 0, 1, then again it's going to be S2, and if it is 0, 0, then S3. And from S3, if it is 0, 1, then it is S1 with the output of 1. Okay, so this particular combination forms the state when the output is going to be 1. Now let us try to see what are the other possibilities, let's try to complete the state machine. Now also try to remember, now since there are two inputs, y and f, so at every state we have to see what would be the possibilities for all the four input combinations 0, 0, 0, 1, 1, 1 and 1, 0. So from S0 we have already seen that what would happen when 0, 1 is there, what would happen if 0, 0 is there, 1, 0 is there and 1, 1 is there as an input. So as these would be our guiding words. So if f is 1, it doesn't matter that what is the value of y, the output state is going to be S0. So we can say if it is 1 and independent of value of y, it's going to be this. So the other possibility is this, that if it is 0, 0, so that means my f value is 0, then 0, 0 would also mean that we are going to stay there in S0 state. So when we are saying 0, 0 or when we are saying x0, so x0 would have both the states 0, 0 as well as 1, 0. 1, 0 is there in this equation, this expression also, but yes, it makes our life simpler. So which means that we can write this the condition as f plus y dash. So f plus y dash, if the condition is f plus y dash, then we can say that it's going to be there in S0 state. So let us see this f plus y plus f0 state is there in S1 also. So let us see in both of these cases it's going to be there in the S0 state. Okay, so we have seen this particular condition, that in case f is 1, irrespective of value of y, it's going to be the S0 state, and this represents 0, 0 scenario. That means f is 0 and y is also 0, then it's going to be in S0 state. So let's look at the S2 scenario. In S2 scenario, we have to see, we have already seen that 0 0 will take it to the S3 state, 0 1 will take it to the S2 state, but if there is 1, f is equal to 1, and irrespective of value of y, it is going to the S0 state. So that means there has to be arrow from S2 to S0 when f is 1 and y is irrespective, y is don't care, output is 0. So what about S3? So S3 case is little interesting because here if my although my f could be 1, but if my input is 1, then it can go to S0 state with the output of 1. Okay, so if f is 1 but input y is also 1, then the output is going to be 1, but it's going to be going to the S0 state. If y is 0, so if f is 0, then if f is 0, that means it's a don't care, then input is 0, input is 0, but it doesn't depend on the f, but it's always going to be the output is going to be 0. So this is how we have to design this state machine. So since we had already designed the state machine without considering f, it was little easier in this case to redesign that and to rethink about the scenarios, what would be the impact of f, and then redesigning the interaction. So this is how we would design if there are multiple state machines or multiple sub modules. So in summary, so before this summary, so essentially what kind of advantage we have got by designing these two state machines independently. First of all, the total number of states has been reduced from 1024 states, we have reduced it to 256 plus 4 states. Along with that, the design of 256 states was easier straightforward because we have designed it using counter, and design of this sequence detector was easier because the first design of sequence detector was independent of f. So and based on that we have inferred couple of rules, and those rules when we implied on our state machine, then we could design the effective state machines with both the interface input as well as the original input. So overall design was easier, first of all, efficient in terms of area, and in terms of designing also it was much easier than designing it using a single state machine. So the overall summary is that whenever we are designing any complex system, if we define them into subsystem, the key in defining subsystem is any two parts which seems to be independent, which has very less interaction, or which has very definite, well-defined interaction, can form two different submodules. Okay, so because they have well-defined interaction, so that well-defined interaction can be formed using interfaces. We can clearly define what are going to be the inputs, what are going to be the outputs of each submodule, and how they would interact with each other, what would be the behavior, semantics. Or semantics means that whenever input is 1, what is its meaning, and whenever input is 0, what does it mean. So that interface, semantics and behavior, if we identify, then we can design all these submodules individually. So this particular information, sometime it helps, sometime it doesn't help, but in our case, which we took, it was quite effective that we can design this submodule without considering the interface. Okay, so once it is designed, so that means we know if it's a standard kind of a design, then we can design it without considering interface, and after that, considering interface, we can reiterate the design process. So because our first level of design without interface is already there, so adding the interface part of signals could be easier. So that's why it can help many times. Okay, so this is end of this particular topic. So let's try to do couple of tutorial problems related to this kind of interactions, and we'll see you in the next lecture. Thank you very much.